Hey everybody, it's Friday, October 2nd. As you can see here on the screen, today's aim is for us to focus on how we can use relationships between kinematic quantities like position, velocity, and acceleration to make translations between graphs. And so for the majority of today, we are going to be focusing on that. Before we get to that, though, I want to have you take a look at one more sheet to have you get a little more practice with the kinds of calculations that you're going to have to do for graphing problems. So attached to the post with this video, there should be a PDF entitled AP Physics Graphical Representations of Motion, Cheetah Velocity versus Time Graph. I'd like you to go and open that up. And for this first bit, I want you to pay attention specifically to part A. So obviously you can see here the graph that's shown is a graph of velocity versus time. And the question says, in part A, assuming the cheetah started its motion at the origin of a coordinate system, does the cheetah end up to the left or right of the origin? Explain your reasoning. And then there are some lines there for you to explain your reasoning. So I'd like you to pause this video and take 1 or 2 minutes to just observe the graph, think about what you're seeing, and then maybe another 2 or 3 minutes to come up with an answer and write it down. So I want you to pause this video and take about 5 minutes to answer this question, and when you hit play, we'll go over it. Okay, so it's important to realize when they ask you questions about whether they end up to the left or the right of the origin, essentially what they're asking you is the displacement of this object positive or negative? Now, there are a couple of ways that you can figure that out, the most obvious of which is by just like straight up calculating it. But it's important, especially for the AP test, that you get a feel for how you can answer these questions without having to do calculations. And so if they're asking you if the displacement is positive or negative, and this is a velocity versus time graph, you need to think about the area under the curve. And so if you look at the graph here, all of this area shaded in blue is what we can refer to as positive area. Remember, the area under the curve is the area bound between the line on the graph and the x-axis. So that would be all of this area here shaded in blue. But of course, if we're talking about the whole 22-second time interval, then we also need to talk about the area over here, shaded in red. And notice, because this area bound between the line on the curve, the line on the graph, and the x-axis is underneath the x-axis, then technically the area there is negative. And so the question is there more blue area than red area, or vice versa? And I think it's pretty clear from looking at the basic sketch here that there's more blue area than red area. And so since there's more blue area than red area, the overall area under the curve will be positive. And since the area under the curve represents displacement, the overall displacement will be positive. And so looking at the answer key, your work, or your answer should look something like this. What I wrote is the cheetah ends up to the right of the origin. Since the displacement is determined by the area under the curve of the velocity versus time graph, and the positive area under the curve is larger than the negative area under the curve, the overall area under the curve is positive, which means that the total displacement is positive. And so we can wrap that up by saying, since the cheetah's total displacement is positive, the cheetah will end up to the right of the origin. And so notice here, you're stating the principle and you're applying it to the problem, and then you're tying it all together. That's the basic format for how you explain these things on the AP test. You state the principle, you apply it to the situation, and then you basically explain how the principle informs you about this particular situation. If you want to write that down, I suggest you take a second to pause this video here, and when you hit play, we'll move on to the next one. Okay, so for part B says determine the displacement of the cheetah over the 22-second time interval. So you'll be able to confirm this, your answer to part A, for sure by doing this calculation. Now, the fact that it's over the 22-second time interval means you have to do all of the positive area and all of the negative area. And I'm sure what a lot of you are thinking just looking at this is, wow, this is really annoying and tedious because there's a lot of different shapes. And while that's true, I think the reason why I want to give you this one as the first one I really want you to practice on your own is because that's really the only reason why people get these wrong. When I give these on tests, they're usually not as complicated, but whenever people get them wrong, they get them wrong for careless mistakes or for like failing to keep track of things appropriately. So as you're labeling these shapes, you should be labeling them things like 1 and 2, and just make sure you're keeping track of all the things. If I were you, the first thing I would do is I would make sure you are deciding exactly which shapes you're finding the area of, and then do the calculation. Because this calculation is so tedious, I want you to go ahead and pause this video and work on this for, let's call it like 8 or 10 minutes. Solve the whole thing, get the answer, and when you hit play, we'll go over it. Okay, so like we said, doing area under the curve calculations are not actually hard. The thing that you need to watch out for about these is that they're annoying. You have to make sure you are keeping track of all of your shapes appropriately. And so I want to go through that here first before we actually show the work. So because these things can be so annoying, like I said, I think it's a smart idea to remember the area of a trapezoid formula. The area of a trapezoid is the average of the bases times the height. So this part is what I called base 1. This part is what I called base 2. And then here the height is 5. Now, if you're looking at this next shape, this whole thing here, the rest of the positive area, that's not a trapezoid. And so what you need to realize here is that you need to break up this part from C to D, basically, into a triangle and a rectangle beneath it. And so, because that's the only rectangle I have so far, I called one of these dimensions L1 and the other one width 1. And then for my triangle, because I already called that base 1 and base 2, and the height of this one is going to be height 1, I decided to call the dimensions for this triangle BCD for the base, because this is triangle CD here, really, where the points, the line connects on the graph, and then I called the height HCD. How you do this, we're not really going to go nuts about, just as long as you make it clear. So notice now I have 3 shapes. I have this trapezoid out in the beginning, I have this triangle, and this rectangle. Then I decided, and I'm going to change the color here just so the contrast is clear, I decided to call this whole thing a trapezoid, just to make my life easy. So that whole area shaded in red is a trapezoid. And then this whole area shaded in red is a trapezoid. Notice you don't need to break it up into 2 triangles and a rectangle. That's a little tedious. You can just call it a trapezoid and be done with it. And so your work should look something like this. So this is a lot of work and it could be a little hard to follow, so I just want to make sure I'm going through every single piece. Base 1 is 6 seconds. That would be the bottom from here to there. The base of that first trapezoid is 6 seconds. I called base 2 4 seconds. So that would be the top base, so to speak, from B to C. Notice it goes from 2 to 6, so that's 4 seconds. Then I call the height of this trapezoid H1, which goes from 0 to 5. So the height which I called h1 since that's the first height I'm talking about, is 5 meters per second. Notice putting the units in there correctly really matter. And so I'm going to go through this bit by bit, talking about all of them separately, just so it feels like it makes a little more sense. The area of that trapezoid is the average of the bases, 1/2 b1 plus b2, times the height h1. So b1 is 6, and b2 is 4, and 6 and 4 is 10. 10 times 5 is 50, and then half of 50 is 25 meters. So that's the contribution from the first shape. Okay, moving on. My next shape is this rectangle beneath the triangle. And so the width of that triangle, length and width are interchangeable. So notice this way, it goes from 6 seconds to 8 seconds. So that would be 2 seconds. And the other way, it goes from 0 to 5. And so that would be 5 meters per second. So notice I called L1 2.0 seconds, and I called width 1 5.0 meters per second. The contribution to the area for that piece is just L1 times W1, because the area of a rectangle is just length times width. And so I plugged in L1, 2 seconds, plus width 1, 5 meters per second, and obviously 2 times 5 is 10, so that contributes 10 meters to the total area calculation. The next piece is this triangle. And the most important thing to realize about this triangle is the bottom of the triangle goes to there and extends to there. So I can't make a triangle piece with this selector tool, but that triangle that's inside the blue box is the triangle we're talking about. So notice its base goes from 6 to 8, so that would be 2 seconds. The height is the tricky part. The height starts at 5 and ends at 30. So the height is 30 minus 5, which is 25. So notice I called that BCD because I'm going to refer to that triangle as triangle CD. I called the base of that triangle 2 seconds, 2.0 seconds, and the height of that triangle is 25 meters per second because the height goes from 5 to 30, making it 25 meters per second tall. And so the area of that triangle is 1/2 base times height, and so that's why I wrote 1/2 BCD times HCD. And so the contribution to the total area is 1/2 of that base, which is 2 seconds, times the height, which is 25 meters per second. 2 times 25 is 50, and half of that would be 25 meters, and so that's written there as 25 meters. So notice so far we have 25 and 25, which is 50, plus another 10 is 60. So up until 8 seconds, the cheetah had gone 60 meters. Okay. Now remember, in that drawing I made before, everything that's covered in this blue box here, this trapezoid, I'm just going to do as one shape. So notice the base over here, the bottom base, goes from 8 to 15. Notice it goes to the middle of these two lines labeled 14 and 16. So it goes from 8 to 15. And so that's 7 seconds long. The top base goes from 8 to 10, and so that would be 2. So the bottom base is 7, the top base is 2, and the height would be the full 30 meters per second. And so I wrote here, I called the bottom base B3, that's 7 seconds. The top base I called B4, because that's my fourth base, and so I called that 2.0 seconds. And then the height is the full 30 meters per second. Since that's a trapezoid, its contribution to the total area is the area of a trapezoid formula, the average of the bases times the height, which is 1/2 times B3 plus B4, that's the average of the bases, and then times the height H2. And so when you plug it in here, and I had to show this on the next line because this calculation is kind of annoying, you have 1/2 of 7 seconds plus 2 seconds, and then times 30 meters per second. So 7 plus 2, we'll do that part first. 7 plus 2 is 9. 9 times 3 is 27, so 9 times 30 is 270. And then when you take half of that, half of 270 is 135. So notice, up to this point, we said the cheetah had gone 60 meters. And then by the time the cheetah stops for a brief instant at 15 seconds, the cheetah's traveled 135 plus 60, or 195 meters forward. And to wrap it up here, the last shape from 15 to 22 seconds is just a trapezoid, that trapezoid in the blue box here. And so we just have to find the area of that trapezoid. The bottom base goes from 15 to 22. So again, that's 7 seconds. The top base goes from 17 to 20. And so that would be 3 seconds. And then the height is negative 15 meters per second. It's super crucial for everybody to remember that when the line is below the x-axis, the area is negative because it's below the x-axis. The area under the curve is defined as the area bound between the line on the graph and the x-axis, and so the area under the curve is negative. So I have base 5 is 7.0 seconds, base 6 is 3.0 seconds, and the height, h3, is negative 15 meters per second. The area of that trapezoid is 1/2 b5 plus b6. That's the average of those two bases, and then times the height, h3. And so plugging that in here, I have 1/2 of 7 plus 3. That's the average of the bases, and then times negative 15. And so 7 plus 3 is 10. Half of 10 is 5. And then 5 times negative 15 is negative 75. And so if you take the 195 that we found up to 15 seconds and then subtract the negative 75 for the negative area under the curve from 15 to 22 seconds, you get your overall displacement, which is 120 meters. I'm going to leave the whole solution on the screen for a second, just so if you want to pause it here, you can take a second to review the work. And once you're done looking it over, you can hit play, and we'll move on to the next question. Okay, then moving on to the last part here. Last part says, Part C, determine the acceleration of the cheetah during the 10-second to 17-second time interval. So determine the acceleration of the cheetah, basically here from E to F. Now, I want to be clear. Whenever it is a graphing problem, and I am asking you to find something from that graph, I want you to use graphing techniques to find it. So take a second to pause this video, go ahead and calculate that acceleration, and when you hit play, we'll go over it. All right, so part C asks you to find the acceleration during the 10-second to 17-second time interval, so that would be this line here from E to F, and your work should look like this. So just to explain what I was saying before, when the day comes where you will have a graphing test, the test is going to assess your ability to use graphing skills. And so obviously, while you can find the acceleration using the acceleration formula, I want you here to show the work using the slope equation. So the first point I picked was basically point E, which notice is 10 seconds and 30 meters per second. And so whenever you write points, you always write them as x comma y. So I wrote 10 seconds comma 30.0 meters per second. And then for my second point, I used point F, which is 17 seconds comma negative 15 meters per second. My slope m is equal to the acceleration a. And so basically here you just go through and you plug it in. The slope formula is y2 minus y1 over x2 minus x1. So we write that first, and then we plug into it. So I have negative 15 meters per second minus 30 meters per second. So that's negative 45 meters per second. And then the denominator, I have my x2 minus x1, 17.0 meters per second minus 10.0 meters per second. And when you do that work, you get negative 45 over 7, which gives you negative 6.42857, and then more stuff in your calculator. And so to three significant figures, which notice all of the numbers in the graph are given to three significant figures, we'll call that negative 6.43 meters per second squared. So that should make sense to you here, because notice when that negative acceleration interval starts, the object had a positive velocity. And so the positive velocity combined with the negative acceleration caused the object to slow down, then stop, and then start to accelerate in the negative direction, where they increased the velocity in the negative direction. And that's the idea. The acceleration is negative 6.43 meters per second squared. All right, if there's anything you want to write down from there, go ahead and do that now. And if not, then that's it for this sheet. And for the main graphing practice section, for the rest of the video, we'll talk about graphing translations. Okay, so like I just said, the rest of this video is going to be devoted to talking about graphing translations. Okay, so the first big question here that we have to ask is, what is a graphical translation? And the answer here is pretty simple. A graphical translation, and this is not like an official title, by the way, this is just something I call it. A graphical translation is a type of problem where you are given a graph for one of the kinematic quantities. So that could be anything like position, distance, speed, velocity, or acceleration. And you're asked to sketch a corresponding graph for another kinematic quantity. So they'll give you a position versus time graph, and they'll say, draw the velocity versus time graph for this position versus time graph. And so we're going to talk about how to do that. This part's very important, though, because obviously you have to know what it is. So take a second to pause this video and write that down. And when you hit play, we'll move on. Okay, so what can we say about how to do this? Your first most important note here is you use the concepts of slope and area under the curve to make a basic sketch of the graph. Now, the reason why I'm saying use the concepts of slope and area under the curve, because really what you're going to be doing is you're going to be looking at the graph they give you, looking at the graph they want you to draw, and then you're asking yourself, how are these two things related? So for example, let's say they give you a graph, and this is going to be like the easiest possible example. The ones that we're going to do are way harder than this. But let's say they give you a graph of position versus time, and it looks like this. And they say, question, draw the corresponding velocity versus time graph. Your job is to ask yourself the question, how do I find out information about the velocity, which is the graph I'm trying to draw, from a graph about the position, which is the graph you're given? The answer is not like some big mystery. You should all know by now the slope of a position versus time graph is the velocity. And so that's what I mean by use concepts of slope and area under the curve to make a basic sketch of the graph. If they said to draw this graph, you would say, okay, well, the slope is the velocity, and the slope of that position versus time graph is constant. So the velocity's got to be constant. Boom. That's it. That's really all we're talking about here. Your second job is to look at the magnitude of the slope or area under the curve to make judgments about the approximate magnitude of the quantity on the new graph. This part you're not supposed to go nuts about, but let's just say here that after this part of the graph, it went like this and then continued with like a much larger slope. I know it looks like that is straight up, so let me make it a little more slanted. So like, let's say there was a slanted line there that wasn't straight up. It's like, we'll show it there, and there's like, whew, bigger slope. That looks almost the same now. Geez, I'm having trouble with this pen today, but you get the idea, bigger slope. So then you would come back here and you would say, okay, well, for a brief moment there, the velocity drops to 0. But then afterwards, the slope is actually a little higher. So we should make the velocity higher. You'll get a feel for what that second note means when we get more into these more complicated problems. This is a very important point. Since these are qualitative sketches, meaning you're not actually using numbers, your graph only needs to reflect general trends. So the point here, like in that last pretty bad example I gave, is if that second slope, let me go back, if that second slope was twice as high as the first slope, there's no way that you could know that because there are no numbers on the graph. So you're not actually going to have to go nuts about, okay, wait, this line's got to be twice as high as the other one because the velocity is twice as much. You just need to show that it's more. That's what I mean by general trends. If one thing is larger than the other, if one thing is increasing, decreasing, or remaining the same, you don't need to go nuts about the numbers. That's a big important point because you don't want to mess yourself up by trying to get too into the weeds on the size of these numbers. All of the template graphs, meaning all the graphs they want you to use to sketch your other graphs, all of the given graphs are not going to have numbers on them. So your graph only needs to reflect general trends. All right, I think it is certainly the case, and you'll have to be the judge of this year, but I think it's certainly the case that every time I start to talk about this, kids are super confused. The real name of the game with these kind of problems is all about practice. And so I think you'll start to get the hang of these when you see me show some more examples and you do some examples on your own. Before we do that, though, I just want to say one more thing, which potentially could make this a little more confusing, but I'm going to try to have us focus on this point every time we get to one of these examples. Okay. This is not a calculus class. As a result, we only deal with constant accelerations in this course, meaning the velocities in all of these problems will always change at a constant rate. However, because the textbooks that we are using don't necessarily operate under that assumption, I want you to remember, assume the object's acceleration is constant, unless the graph is drawn in such a way that you can't. If there's a velocity versus time graph that's curved, then you can't get around that. But if there is a position versus time graph that's curved, which remember, position versus time graphs are always curved for accelerations, then assume the curve is curving in such a way that the acceleration is constant. Because it's impossible to tell that without numbers, right? Because the position versus time graph for an accelerating object with a constant acceleration, if you had numbers, like would look something like this. And if it had an increasing acceleration, it would look something like this. And there's no way to be able to tell the difference between those without numbers. Like obviously if they're plotted on the same graph you could, but if they're not, then you can't. So the basic assumption here is you're always going to assume it has a constant acceleration unless you really, really, really can't. Take a second to pause this video to write that down, and when you hit play, we'll go ahead and take a look at a couple of examples. We have no choice here but to practice a couple of these things, so let's look at an example. This example is in the one-dimensional motion packet. It's on page 17, number 22. Page 17, number 22 shows this graph. And it says for each of the position versus time graphs in figure Q1.22, which is this figure, draw velocity versus time graphs and acceleration versus time graphs. So my basic advice is do one at a time. Let's start with the velocity versus time graph. So the first thing you're going to want to do, and I already put these in here so I didn't have to waste time on the video. The first thing you're going to want to do here, and I guess I'll do this in red. The first thing you're going to want to do is you're going to want to set up your axes and label them. This is going to be the velocity versus time graph. And my recommendation, and you're going to have to feel this out as best you can, but my recommendation is to make this line up with the graph you're drawing from. So they give you the position versus time graph. It's in the packet. I recommend you sketch it in your book. And then you draw the velocity versus time graph axes right underneath it. And where it says T1, you make a mark there on the axis that says T1. Then you go T2, and right underneath, you mark T2. This is a lot easier if you use a straight edge. Right underneath, very close to T2, you write T3. Then you have T4, then T5, and lastly, T6. Okay. So keep in mind that maybe you just want to make the markings and not actually write T1, because where you put the numbers on the axis might get in the way. Okay, so what's the first thing that you should think about here? The first thing that you should think about here is that this is a graph of position versus time. So your first question is, I am drawing a graph of velocity versus time. How do I get information about velocity from a position versus time graph? And the answer is you get it from the slope. And so really you're just looking at what's happening to the slope, because whatever is happening to the slope is happening to the velocity. And further, whatever you can say about the slope, you can say about the velocity. So from 0 to T1, what can we say about the slope? Well, the slope is positive and the slope is constant. So that means because the slope represents the velocity should be positive and constant until time T1. Then from T1 to T2, the slope is 0, which means the velocity is 0. Now, all of these lines are straight, and so this graph is not really showing that much acceleration. So we are going to use here what we refer to as discontinuous functions. From T1, the way this graph is drawn basically makes the velocity automatically drop to 0. So the way we do that is we draw a dotted line, and I'm going to connect it to the next line. And then the velocity is 0. Notice when your velocity is 0, you want to make that like really dark, because you have to cover the axis. Especially, I have the ability on here to use different colored ink. If your axis is drawn with the same color as your line, you just kind of color it in here like a crazy person, and then you're definitely able to see that that's not just the x-axis, but rather it's the line on the graph showing you 0. Okay, so from T2 to T3, and then continuing from T3 to T4, the slope is constant because the line is straight, and the slope is negative. So we need to show a constant and negative velocity. Now notice this is what I referred to before. This is actually why I did this, so you could see the point. These are now in the way. So if you use a pencil, you can just get rid of them. But if you don't have a pencil, then you can just make the tick marks, and you just have to look, up here to label them. So the velocity is constant and it's negative. So I'm going to draw this discontinuous bit, and I'm going to make that go all the way up, constant and negative, to T4. Okay, so now from T4 to T5, the slope is 0, so the velocity is going to be 0. We'll just do that coloring again, make it nice and dark. And then from T5 to T6, the slope is positive. Now here's where the second part comes in. If you were paying attention, you realize that's only the first part. The first part is to just make your sketch. The second part, and I'll go back and show this, is to look at the magnitude of the slopes and make judgments about the approximate magnitudes of the quantities on the new graph. So what does that mean? I hope it's obvious to everybody that the slope here is definitely smaller in magnitude than the slope here. Look at how much more that line is slanted. So my graph has to show this velocity being bigger than this one. And it certainly does. If you really wanted to go nuts about it, and that's why using a pencil for this is crucial. If you really wanted to go nuts about it, you could go back with a pencil and edit and just say, oh, that velocity really is lower. So let's just go ahead and make that lower. Okay, so that's part one. And then over here, I think the crucial detail to notice is that there's like a symmetry here in this shape in the bottom. In the same amount of time, you have the same change in the y-axis variable. So those slopes are the same. And the fact that the slopes are the same tells you you need to make the heights of those velocities, that would be here and here, the same. And the height for that velocity is definitely wrong. I made it too small. So then all you have to do, you know it's supposed to be constant already. So you just go and you erase. And then you say, oh, I just need to make that a teeny little bit higher. No big deal. And then you like take your finger, you measure it out to make it equal. And then that's it. Now, it's hard for me to see on the computer whether those are equal, but if you're using paper, then it's easy to just go and look. I'll try to use this, I guess. It's like 1 eraser, 2 eraser. It's like 3 erasers high. So it's like 1, 2, almost 3 erasers high. So that's the idea. And that's it. That's the first graph. Now notice, this question also asked for us to draw the acceleration graph. Now, the reason why I gave the advice before, you should do these one at a time, is because you can't get any information directly from a position versus time graph about the acceleration, but you can get it from the velocity versus time graph. So if they ask you using a position graph to just draw the acceleration graph, I draw the velocity graph first and then draw the acceleration graph from the velocity graph, because it goes in order like that. The slope of the position graph is velocity. The slope of the velocity graph is acceleration. So this one's easy because notice all of these slopes are 0. And so your acceleration graph, remember my velocity graph was down here. Let's just imagine that that was drawn. The acceleration graph is a piece of cake. It just looks like this. And again, you can use a ruler, make it nice and straight. It's always 0. And that's it. Only when a position versus time graph shows curves is the acceleration non-zero. And that's it. Now I want to move on to a couple of other ones. But before we do that, I just want to remind you a very crucial reminder. This crucial reminder says in this course, we only deal with constant accelerations. So if the velocity versus time graphs have a non-zero slope, they should still be constant. And so notice we did that. Now here, the slope was 0. But even if the slope is non-zero, because there will be an acceleration, if you're drawing them, you should just draw them with constant slopes. Even if the velocity versus time graph is given to you and it doesn't have constant slopes because it's like rounded and curved a little bit at the end, you should just assume that it looks boxy for our purposes because we only deal with constant accelerations. Again, all we're really trying to capture here is general trends, and so I don't want you to go too nuts about that. On that note, let's take a look at another example. This example, I just want to be clear about this first. This example is from the 1D motion packet. This set of graphs is on page 16. The question is number 6. However, number 6 is not asking you to draw graphs. I think it's saying, like, if this verbal description describes the motion of an object, then which one of these graphs is the right graph? But because it is a printed graph that will work for this purpose, we're sort of repurposing these graphs for these kind of questions. I'm actually going to ask you to do that a lot on the homework because there's not a lot of these in the packets. So, like, as I already mentioned once in one of these earlier videos, like, if they ever ask you something about, like, describe a realistic motion story, I don't want you to do that. It's a waste of time. But if that's all the question says, then I will probably just say, page 16, number 6. Forget what it says. I actually just want you to draw the graphs or something like that. So on page 16, number 6, they ask you about some nonsense, but they give you some good graphs. So let's go ahead and take a look at those. This is a velocity versus time graph, and we're going to just say, because we have both of these things here, that we should draw the position versus time graph and the acceleration versus time graph. And so we'll start with the position versus time graph. Now, there are a couple of ways that you can do this. I actually want to go back for a second. I said in a note before is that you can use concepts of slope and area under the curve to make a basic sketch of the graph. Whether you use slope or area under the curve, though, is entirely up to you. I'm going to do this first one both ways. We'll talk about the area first. So it's important to realize, notice this part is curved. But what I was trying to tell you before is, like, let's just assume that's a straight line and then it's just a sharp decline. So we don't have to worry about the curvature. So I hope everybody is with me that the area under the curve here in the beginning is a rectangle. And because this is a velocity versus time graph, the area under the curve gives us the displacement. And so thinking about this in terms of the area under the curve would work as follows. So you would say, okay, after a little bit of time, the area under the curve is this slice of the rectangle. And then after another little bit of time, it would be both of these slices, 1 and 2 of the rectangle. And after another little bit of time, it would be another slice. And notice, the main thing to notice about these slices, so to speak, of the areas is that they're the same size. And so the idea here is, as the time goes by, if we wanted to call this like T1, T2, T3, as these equal time intervals go by, the area under the curve is growing, and it's growing at a constant rate. And so that tells you that the position, and really because we're representing the displacement here, should be increasing at a constant rate. Now you can make some assumptions here. I always make the assumptions to make my life easy. Do we know that the object started off at the origin of the coordinate system? No, we have no idea. But why not just assume that it did? Because it doesn't tell us anything otherwise. You could start the graph from up here if you want, or from down here if you want. But to make your life easy, if they do not say otherwise, I always assume the initial position is 0. And so because we said here that the area under the curve is growing at a constant rate, we have the object's position increasing at a constant rate. We stop there, and then that's good. Now the graphs line up. Now, in some cases, the area under the curve method is like the harder method, but it still works. So like if you just wanted to use the slope method is like really the check for the area under the curve method. So like let's say we got rid of this, but we know what we said about the area under the curve, right? We said the area under the curve is growing at a constant rate, so that means the displacement should be increasing at a constant rate. But let's do it backwards now. This is a position versus time graph. It gives us information about the velocity. Since here, the slope of this graph is constant and positive, that would tell us that the velocity is positive. And what do you know? The velocity is positive and it's constant. So that's the idea. Basically, I personally, I think it's a little easier, but if the area under the curve idea works for you, then do that. I think it's a little easier to say whatever happens to the velocity on this graph, that needs to happen to the slope. And so because because the velocity is constant here and it's positive, then I need to draw a graph that has a constant to positive slope. Boom, and then you're done. That's the idea. Okay. Now this next part is kind of hard because from here, which we just had it drawn, to there, and I'll just mark that here more or less, right there, we see on this graph that the velocity is decreasing. And I just want to get rid of that. But we see that the velocity is decreasing. And so as we just said, whatever is happening to the velocity should be happening to the slope of this graph. And so that means we need to draw a line with a decreasing slope that eventually, by the time it gets to here, reaches a 0 slope. These are kind of tricky. It's a pain. I'm going to show you the smartest way, I think, to do it. Now, this is going to be particularly tricky because I'm trying to draw this on the computer, but bear with me, please. So the first thing I am thinking is that I need to draw a line with a decreasing slope. So that's going to look something like this, right? Because the slope of the tangent line is leveling off, so to speak. And if it's getting more horizontal, that means the slope is decreasing, right? So I need to draw a line that looks like that. But also notice the velocity immediately decreases. It doesn't go up first and then down. So what I see a lot of people end up doing, I'm actually going to draw this in a different color to make my point. A lot of people end up doing something like this. But notice that shows the velocity getting almost to infinity and then leveling off. And that doesn't make sense, right? So what I do, and like I said, I think this is the smartest way to do it. If you disagree, then you'll need to figure out your own way. What I think is the smartest thing to do is to take the line I had and I like to make it an extended dotted line first. And so there's my sort of horribly drawn extended dotted line. Remember, my graph ended here, though. So I'm actually going to go in and erase that bit just so I don't confuse them. Okay. So basically, when I'm drawing this curved line, I can never have it, and I'm going to do this in blue again, I can never have it go on the other side of this line. It's got to curve away from that line is the idea. Because if it goes over that line, that would show an increasing slope, which is just simply not happening. So to do this, well, I'll just take my pen and I'll draw a curve that will eventually reach a slope of 0 by here, let's say. And so I'll go shoop. and then it's done. So if you make these connect a little better, which it's difficult to do on a computer, but you'll probably have an easier time doing it with a pen, and then you just erase your little guideline, now you have a curve that hopefully looks okay. And that's the idea. You want to just make sure here that you don't allow it to go back down before you get to this point, because then it's going to show the object changing direction. Now, of course, lucky you, that's actually what happens here if you did that. So now the velocity is increasing in the negative direction. And so we need to have the slope increasing in the negative direction there. To there, I mean. And so we'll, starting from where we left off, we'll just have the object decrease its velocity in the negative direction. And now here you want to try to draw these things as smooth as you can, but it's important to understand there's going to be some limitation to it. You don't want it to end up straight down at the end, because straight is like a super high velocity, or it's undefined if you do it exactly straight down. And so it should just look something like that. Again, we're not going to go nuts about this, number one. And number two, this is not an art contest, but that's the idea. Now, I'm sure some of you are thinking, wait a second. Why did you do this? And I'm going to try to freehand this in one shot here. Why did you do this instead of this? Straight, and then the curve, and then down all the way to the axis. That's a decent question, because a lot of people feel like that should come down to the x-axis. But I can tell, looking at that graph, it shouldn't. Because if we look, remember we were talking about this yesterday, the negative area is nowhere near as large as the positive area, which means the object was traveling in the positive x direction and did not make it back to the origin. Because if it made it back to the origin, then the negative area over here would have canceled the positive area, but it didn't even come anywhere close. So it was going forward, going forward, going forward, going forward, but getting slower, going forward, but getting slower, stopped, and then went backward, but not in an amount that was anywhere close to the amount that it went forward. And so it's still got to be way above the x-axis for this to be considered correct. That was long. These take practice. I promise you will get them. You know what is supposed to happen if you know what slope and area under the curve for these graphs mean. Getting the hang of drawing them and noticing the patterns and like even learning the shapes. Because if you by some point when you see a graph that looks like this, you will say, oh yeah, that one looks like this, because you've done it before. And so I want you to trust in the process and not freak out if you're watching this and you feel like you have no idea what I'm talking about, because I'd imagine we're going to be talking about these things in some Zooms, because this is a bit of a pain. Okay, luckily, the acceleration one is very easy, because the acceleration of a velocity versus time graph is the slope. And so from 0 to whatever time this is, I guess we'll just make a time on here. We'll just make a little mark. The acceleration is 0 because the slope is 0. So we'll just do this thing again. We color over the axis dark enough so that we can see our line and we're in business. And then here, the slope is constant and the slope is negative. So we draw these dotted lines showing our discontinuous function. And then we just have a nice straight horizontal line. Ah, that's not horizontal. Those of you who had me in honors physics, for those of you who didn't, I'm sorry. Those of you who did have me know how just garbage I am at drawing. I'm trying my best here. And it's constant and negative, and that's it. So you draw the discontinuous functions always with these dotted lines, because that's how they're supposed to look. And that's that. Questions? I would imagine you have questions. Please put them in the comments if you have them. Talk about the timestamp in the video at this point. Talk about why the line didn't go like this, why the line didn't go like that. If you are planning on going through the rest of this year without asking questions, this is going to be a rough one for you. So please, please, please ask about this if you feel you need to. Let's take a look at another one. Before we do that, though, I guess, let's write down one little thing. When going backwards, like when translating a velocity versus time graph to a position versus time graph, whatever is happening to the second graph, the velocity, should be happening to the slope of the first graph, position. And when I say first graph, second graph, third graph, I'm saying position is first, velocity is second, acceleration is third. So the area under the curve method sort of works, but as you can see there with that second part of the graph, I'm going to come back to this in a second. With that second part of the graph, when the line comes down, it would turn into a nightmare, because you'd be saying like the area is still positive and it's increasing, but it's increasing by less and less and less and less every second. So the displacement should be increasing by less and less and less every second. Notice that's actually what's happening. But then because the area is negative, the area under the curve should actually be getting smaller, and so that means it's got to become like it's a nightmare. So the best way to do it is by thinking about the slope. And so it says here, when going backwards, like when translating a v versus t graph to an x versus t graph, whatever is happening to the second graph, so like the velocity graph, should be happening to the slope of the first graph. Take a second to write that down, and then we'll look at one more of these. Okay, so this one is showing you a velocity versus time graph. Now, this is actually a fairly common example, so I want to skip this one. Let's go here to part C. And part C says this is a velocity versus time graph. Let's pretend this is what the question says. And it says to draw the position versus time graph and the acceleration versus time graph. I feel like we got off to a rough start with the last one, because the position versus time graph is always harder than the acceleration versus time graph. So let's just go ahead and do the acceleration graph first. One thing I'd like to point out to you also, which may be helpful for you, is when things change, like you can make your own marks. Call that T1, call that T2. And then on your own graph, you can say, yeah, it looks about that long, right? That's T1, and then that's T2. To give yourself some guideposts. So this is a velocity versus time graph. You ask yourself, what is the relationship between the velocity versus time graph and the acceleration? Or in other words, how do I find out information about the acceleration from the velocity versus time graph? The answer, of course, is the slope. And so the slope is constant, and the slope is 0 before T1. And so we make the acceleration 0. And I'll put this over here, T1. And now here we see from T1 to T2, the slope is constant and the slope is negative. And so the acceleration should be constant and negative. And even though the graph here actually does show a slight curve, we'll just assume it's sharp because we only deal with constant accelerations. And so we've got our discontinuous function there showing us our negative acceleration. And the last thing to pay attention to is that the last acceleration is constant and positive. And because of this like V-shaped symmetry here, it's going to be the exact amount in height as the other one. Yeah, I think that looks good. Again, you're drawing for general trends. When we were in class, under no circumstances when I was grading this on a test was I ever like taking out a ruler and saying like, is this high? Is this that? That's crazy. We're looking just for general trends. When I looked at that, if you wrote that on a test, I'd say 0, negative, then positive. Are they about the same height? Now, looking at it, at least to me right now, it looks like this one's taller. But it's not taller by much. So like, whatever, we're not going to make a big deal about it. That's the point. Okay, so the position versus time graph one is a little annoying. So I'm going to have this start at the origin just to be normal. And I am going to look at the velocity versus time graph, and I am going to notice that in the beginning, the slope of the velocity versus time graph is 0, but that doesn't tell us anything about the position. I have to read about what's happening to the velocity itself. And so in the beginning, the velocity is constant. And because the velocity is the slope of this position graph, that means I need to draw on my position graph a constant slope up to t1, which looks about there. And so I'll call that t1. Then my velocity decreases to 0 by t2, which I guess I'll just call there, but less terribly. So because the velocity is decreasing to 0, hey, you already saw this. Remember? We just did this. So this is what I mean by this. Like, you got to sort of take these one problem at a time. You'll start to notice trends. Remember, when an object has its velocity decreased to 0, that means the slope of the position versus time graph has to decrease to 0. That's a little annoying, but it is what it is. And so the graph has got a curve in such a way that it levels off. And so here, I'm going to draw this like that. And I'm going to have it level off until it gets to 0. And notice, if I actually have that flat here, this thing wasn't giving me so much response, then the slope would never go above the slope of the other one. And so we're good. It just goes and then it levels off. Should be a little more curvy looking than that in this region, but as we said, close enough. So that's up to T2. We're almost there. So we'll have that up to T2. And in T2, the velocity is increasing. And so we need to draw a position versus time graph where the slope is gradually increasing. So we're just going to do it like that. And that's it. And I'm going to look at this on the test and I'm going to say constant velocity, constant slope, so that's a constant velocity. Decreasing velocity, decreasing slope, so decreasing velocity. And increasing velocity, and so increasing slope, increasing velocity, boom, full credit. The main thing that you want to be careful for, and this is the real shame of you having to watch me struggle through this on the computer, is this part is bad. So you really want to try to make that a smooth transition. It'll be easier for you to do that with a pen or if you just do it at the same time. So like it's constant, then it levels off, and then it smooth transitions up. And so this stuff is going to take practice. I think also it becomes a little more helpful if you use a ruler and you try to rotate the ruler. So notice, I want everybody to actually try that. Even if you don't take a ruler, just like a Post-it note. If you take the ruler and you hold it at an angle and you start to draw a line and then you just rotate the ruler to the right, you'll notice you get a curve. One more time. I'm actually using a Post-it note right now, so that will do. Take a ruler or a straight edge. You just hold it at an angle so that you're drawing a line with a constant positive slope. And then you just start to rotate the straight edge to the right or clockwise. And when you do that, you will get a nice smooth curve. That's like a good thing to remember. A lot of kids in previous years would say like, yeah, I don't have a ruler, but I have a scale for shop. Or they would say like, I have a student ID card, so I can use that. Keep that in mind because that's a pretty useful tip. All right, so obviously you just had to spend a little bit of time there suffering through watching me on the struggle bus with that one for sure. And so that's really going to be it for today. This is always something that takes, or that I like to cover on 2 separate days. because I like to put it in your brain and just let it marinate for a little bit and then come back and talk about it more. So we'll address this a little bit again on Monday. Now, I actually do, though, want to make sure everybody is trying this. The first thing I am going to address in the video on Monday is the answer to this question. And this is what I would like you to submit to me before we go. As I'm sure you can tell from looking at this question, B1 CRT 21, it is on a worksheet. I have not put that worksheet up yet. That is because you are going to work on it on Monday. I only want you to do this question from that worksheet. This is an acceleration versus time graph. And they are asking you to draw the appropriate velocity versus time graph and to explain your reasoning. So this is what I want you to do. First of all, I want you to recognize these lines, these vertical lines here, are what I've been drawing as dotted lines. And so keep that in mind, please. These lines are showing you that this is a discontinuous function. Discontinuous. That looks weird. I'm pretty sure that's spelled right, though. Function. Dotted lines. So it would look like this if I drew it, right? So really, it's just two quick bursts of acceleration. And so I want you to draw the appropriate velocity versus time graph. And then for the explain your reasoning part, I want you to write one sentence about why whatever you drew over here represents that. And that's what you're submitting for the day. All right, everybody. Have a good weekend. And I hope you don't worry about this too much, because I promise you that when we practice this, this is going to make a lot more sense. Take care.